Namaste and welcome to Code Divinity. I am your coding friend Om, and today's problem is problem number 162, find peak element. This is a medium level problem. So in this problem, we will be provided a nums array. So let's take an example 2, 3, 5, 6, 2, 1. Let's plot it as a graph. So our first element is 2, then the next element is 3, then the next element is 5, then 6, then 2, and finally 1. Now let's connect them. Here in this graphical representation, we can see that the element 6 is the peak element as it is greater than its previous element and also its successive element. Thus, 6 becomes our answer and we return it to the console. In this problem, they have also mentioned that we have to find this peak element within log n time complexity, and the elements which are beyond our nums array will always be smaller than the elements which are inside the nums array. That means the peak element is surely within our given input. Now let's see various approaches which can be used to solve this problem. As in this problem we are searching for the peak element, so we have to check for the searching approaches. So there are two basic searching approaches, and that are linear search and binary search. In linear search, the time complexity can range from constant to the size of our nums array, and in binary it can be constant and can go up to log n time complexity. Because in the linear search we have to traverse entire array, and in the binary search we can use branching to find our peak element. Thus, for this problem we will be using binary search. Now let's understand how the binary search works. In the binary search, we fix a starting pointer and an ending pointer, and we calculate mid position using these pointers. This mid position is generally calculated using start plus end divided by 2. But there is a problem to this approach of calculating the mid, because in certain cases the start plus end results into a certain number which exceeds the limit of our integer. In that case, the mid position will not be calculated correctly. So this fails in the edge cases. Therefore, I am giving a smart way to calculate mid position which will never fail even in the edge cases. So to calculate it, we will use the formula start plus end minus start divided by 2. So here first the bracket will be evaluated. Thus ending minus start will give a number within the range, and then we will add it with our starting pointer, and dividing it by 2 will give us the mid position exactly without exceeding the limit. So promise me that you will use this approach in your binary search problems. So we have seen the problem statement, we have checked the various approaches, we have also learned about the binary search and a smart trick to calculate the mid position. Now let's formulate the algorithm. First we will declare start and end pointers. Start will be initialized to 0, end will be initialized to size of nums minus 1. So both of these pointers are set to the extremes of our given input. Then we will start a while loop until start is less than end. In this loop we will calculate mid. It can be calculated using start plus end minus start by 2. After calculating the mid position, we will check if the mid position is greater than the successive element mid plus 1. If the middle element is greater, we will set end pointer to mid, or else we will set start pointer to mid plus 1, and we will keep doing it until start is less than end. At some point, start and end will be pointing exactly at the peak element. So when the while loop terminates, we will return our start pointer. We can return start or end, whatever, because both are indicating at the same position. Now let's check it out on the LeetCode platform. So this is the problem on LeetCode. find peak element. The problem link is given in the description below, so you can check it out. Now let's read the problem statement. They have defined what is the peak element. So it is strictly greater than its predecessor and its successor element. So they will provide us a 0 indexed integer array nums, and we have to return the index. Remember, not to return the value, but we have to return the index of that peak element. They have also mentioned that there can be multiple peak elements. So whatever algorithm you implement, it's not an issue that your algorithm returns a different peak element and someone else's algorithm returns some another peak element. Everything will be accepted here. They have also mentioned that any element which are beyond the scope of our given input will be strictly smaller than the elements in our nums array. So the peak element is surely present in our input. And this is the important constraint that they have mentioned, that our algorithm that we are writing should find the peak element within the log and time complexity. So for this we will be using binary search as we have discussed before. They have given us 1, 2, 3, 1. So we can observe that 3 is strictly greater than 2 and 1 also. So we will return 2. 2 is not the value, 2 is the index of the peak element. In example 2, 1, 2, 1, 3, 5, 6, 4, there are 2 peak elements. First is this 2, which is greater than its predecessor 1 and the successor 1. The next peak element is 6, which is greater than 5 and 4. So whatever algorithm we implement, if answer is given as the index of 2 or 6, both are considered correct. Now let's check the constraint of our problem. So the first constraint says that there will be at least one element and there can be maximum of 1000 elements. Then numbers can range from negative integers to the positive real integers. And they have also mentioned that within our given input, there will be no two elements with similar values adjacent to each other. So this ensures that there will be a peak element existing in our input. Now after thoroughly reading the problem statement, we can start coding our solution. First, we will declare two integers, start and end. Start will be initialized to 0, which is the first index of our nums. Then end will be initialized to the last element, and it can be obtained by nums.size minus 1. Then we will start a while loop until start is less than end. Within this while loop, we will initialize mid, and the mid can be calculated using start plus end minus start divided by 2. Always calculate the mid using this approach. It will always ensure that your mid falls in the range of the integer. Then we will check if nums of mid is greater than nums of mid plus 1. If the mid position is greater than the successive element, in that case we will move the end pointer behind. Else, if the mid position is smaller than the successive element, then we will move the start pointer ahead, and we will keep iterating until the start and end position are indicating the same element, and that element is our peak element. So we will return the position. Remember to return the index of that peak element, not the peak element itself. So here we have completed our coding. Let's check it on our example cases. So our algorithm is working perfectly, and our approach to calculate the mid is also working perfectly here. Now let's submit it to check on all the test cases. So our solution is working perfectly on all the test cases. Promise me that you will use this way of calculating mid whenever you encounter a binary search problem. In this problem, we have implemented the basic binary search algorithm. There is nothing new to it. And binary search is a very quick way to find the element in our search space. I hope you liked this solution and also the trick that I shared today. Please write your suggestions in the comment below. I will meet you in the next video very soon. Thank you so much.